Hello everybody. This will be the first published video of my Surviving APCSP class series. This one's going to be rushed because I just want to get this one out. I did have a few more videos that were supposed to come out last week for FizzBuzz, but I didn't get around to editing those, so this will be this very rushed uh, jump-in explanation of Chapter 3, the efficiency of algorithms. So the material, these notes that you see here are not mine. They have been taken by Mr. Millard or Larry Millard at American High School in 2019 for his AP or Advanced Placement Computer Science Principles class. And I will be explaining this this lesson and giving my own thoughts and notes about it in an attempt to make it easier for some students to understand. So let's start here. So when it comes to the efficiency of algorithms, an algorithm will have some properties that you need to understand. And an algorithm should be easy to understand, it must be elegant, and it must be efficient. All right, so easy, elegant, and efficient. And here's the thing, for it to be easy to understand, it must be maintained and it must be kept current. Okay, so a system that, from like the 40s, from the 1940s will not be as easy to understand as one from like 2019, just because, things evolve and, it's easier to understand things. It also must be elegant. Okay, and an elegant solution will work most of the time. Must work at all times, regardless of the input given to the algorithm, and it must work in an efficient manner. An elegant algorithm must also be written in a very nice way. It must be clean code, easier to understand, and it must be like a beautiful code. And then it must work for as many cases as possible, preferably all of them. If it works for 99.9% of cases or inputs that it's given, that's awesome. Okay, and what is an example of an elegant algorithm? So an example of an elegant algorithm is one that Gauss used. Okay, and Gauss, the story is that he was being really annoying in class, so teacher told him to add all the numbers from 1 to 100. And instead of adding all the numbers from 1 to 100, he's like, hey, I can make 50 pairs of 101 because I can take 100 and I can add 1 to it, so that's 101. I can add 2 and 99 and make another 101, and keep going down that list. He could make 50 pairs of 101. And like this, he was able to quickly calculate that the sum of all, numbers from 1 to 100 is 50 times 101. All right, so that will be an elegant algorithm. Now, um, an efficient algorithm will have is like the benchmark on the system to compare it to other things. Okay, and the way we'll measure efficiency is time and space. Okay, so when it comes to space, you just want to make your algorithm like shorter, more concise, so it doesn't take up as much space. You don't want, some terabyte file just for, to take a picture, right? That's just why you don't need that big of a thing. So to make it more efficient, we'd say that, hey, we'll have like a 1 GB file to run the program to take a picture. So we can measure efficiency when it comes to time and when it comes to space, okay? And when it comes to space, like I discussed, it's about like how big the file is. And then when it comes to time, time is the central unit of work. And when we calculate time in an algorithm, we are going to disregard the things that besides the algorithm. So like how much time it takes to start up, or how much time it'll take to update an index, or how much time it'll put the input. We're just going to look at, when we talk about speed and efficiency of an algorithm in regards to time, how many steps does it take? Okay, so the efficiency of an algorithm, or the steps of an algorithm, will be measured. It's measured in the 3 stages: best, worst, and average case. And the best, and obviously that's what it is. So the best case is that if the input you give, the algorithm only has to run like one time, and it's the algorithm has to run once, and you have your output. The worst case scenarios is the list is if whatever your input you give it is completely messed up, what is the maximum number of steps it can take? And then there's an average between those. So when we compare algorithms, we compare the worst case situation to the other worst case situation. So when analyzing algorithms, in terms of steps and efficiency, there are two main ways to classify them. So one way to classify, so the type of algorithm that you can you can model in terms of a function, or you can map out how many steps it takes is going to be called a polynomially determinate algorithm. And a polynomial determinate algorithm is one that you can model with a function. So if I can say that, hey, if I, if my list is 5 items long, then it'll take, 25 steps for it to finish. So that will be n squared, right? Anything you can model. If you can model how many steps it'll take, depending on whatever your input is, then good job. That's what we'll call a polydeterminate one. Anything that you can map out how many steps it'll take given an input. So another thing, the way you'll measure such things, the way you'll measure how efficient a polydeterminate algorithm is using the order of magnitude, okay? The order of magnitude. And when you have the order of magnitude, basically what will happen is that if I say that, hey, if my list is 5, let's say I can say that I have some list sorting algorithm, okay? So let's say I have we have some list sorting program, okay? In this list sorting program, I have 5 items. Rather, I know that it'll take me n squared minus 4 steps to sort my list. And remember, this n squared minus 4 will be the worst case situation because we always just measure efficiency of algorithms to the worst case. So let's say I have and n equals the number of items in my list. Okay, so let's say I have 5 items in my list. Then it'll take me 5 squared minus 4, which is 21 steps, which is 21 steps to sort. Okay, this is just a random thing I've come up with. Now, what happens when n goes to, 10, right? That'll lead to 96 steps to sort. Okay, and what happens if n equals 9, this big number? Okay, it doesn't matter as the function keeps increasing, as n keeps getting bigger, most of its value or the y, so most of the output or how many steps it'll take to sort it comes from the squared part. So we'll call it so when we have a polynomially determinate function, we'll take the coefficient of the greatest degree and say that's the biggest, that is, if we have an polynomially determinate algorithm, then we'll take the coefficient of the biggest degree, so in the polynomial, the greatest degree, and that's to the degree that's the degree that'll basically determine how the number of steps the function will take. So if we have some function that takes n squared number of steps to sort, then it is to the second degree. If we had it to the third, then this is the third degree. Okay, and you can see this here. Okay, and the algorithm will be called the order of magnitude n. Okay, the order of magnitude n. So basically, what I'm trying to say is that when you can model how big a function, when you can model the number of steps it'll take a function given some input to that function. So if you say, if I have n number of items in my list, it'll take me n squared minus 6 steps to do it. Then this n squared minus 6 will only be most of the output is influenced by the n squared part, so it's to the second degree. All right. So let's see. Continuing on, we have our selection sort, which was in the last section, so I'm not going to go over it too much. We have this, again, order of magnitude. It tells you how the number of steps will be influenced by this n squared function. And now we have the types of algorithms, okay? And I'm going to go over this. So the types of algorithms we're about to discuss are all data cleanup algorithms. So they don't sort anything. They kind of just want to like filter information. And we will be discussing polydeterminant ones, okay? So the first one will be the shuffle left algorithm. And essentially what the shuffle left algorithm do is it'll go through the entire function and be like, hey, if I come across, so let's say we're trying to eliminate 0 for some function. Okay, so let's say we're trying to eliminate 0. So the goal is to eliminate 0 from the function. Okay, if I have some list which goes 1, 0, 2, 4, 5, 6, 8, 0, 1. All right, essentially what I'll do for the shuffle left algorithm is I'll go through my list, okay? When it comes to algorithm, I'll go through the list and be like, okay, we have 1 here. We're like, oh, we have a 0. So essentially, the next step, what it'll do is it will move everything after the 0 1 place left, okay? And what will happen essentially is that that 0 will essentially just be replaced by a 2. So go 1, 2, 4, 5, 6, 8, 0, 1. The algorithm will keep going. It'll go again, it'll pass, it'll go like, okay, 2 is, something other than 0, 4 is something other than 0, 5 is something other than 0, 6 is something other than 0, 8 is something other than 0. But when it comes to this 0, we'll do the same thing, like, well, since this is 0, I need to move everything left. Essentially what I'll get is 1, 2, 4, 5, 6, 8, 1. And what all that happened was that everything left of the 0 was moved to start where it replaces the 0. And I'll have my notes posted on my website, so you can go and check this out and it'll make it a lot clearer. So continuing on, we have our copy over algorithm. And this is a very simple one. It basically says that if we have the same list, let's say we take the same list, okay, so L1, so list 1 equals this, then all that will happen is the algorithm will go through this list and be like, okay, and look at the first one, be like 1. Is 1 is something other than 0, so it'll come here. And we'll be like, oh, 0 is equivalent to 0, so we're going to ignore it. But 2 is not equivalent to 0, so I'll put a 2 here. And then it'll go again and be like, okay, 4 is not a 0, 5 is not a 0, 6 is not a 0, 8 isn't a 0, but 0 is a 0, so we leave 1. So all it did was anything, if it was a 0, it didn't copy it over to the second list. So as you can see here, we've eliminated our zeros from list 1 into list 2. The last one, or the next one is converging pointers sorting algorithm, or data cleansing algorithm. So this one's a bit complicated. So if we have this list, essentially what it'll do, okay, converging pointers, okay. Essentially what it'll do is if we have this list, it will go through this list and be like, hey, look at 1 and be like, okay, we have 1 here, and then we have 0. And what it'll do is that whenever it encounters a 0, it'll swap it with the last place. So it'll take that 1, replace it with 1. So it'll take this 0. Actually, let's change this to a 9. Essentially what it'll do is if we have this list, every time it encounters a 0, it'll go and swap it with that last place. So 0 will place with 9, and it'll become 2, 4, 5, 6, 8, 0, 0. Okay? And then next step, in the same step, it will reduce the list by 1. So 1, 9, 2, 4, 5, 6, 8, 0. Okay? And as you can see, this 0 that was here, so this 0 starts here, comes down here, and then it's gone. Okay, and it'll go through the algorithm. It'll go through the sorting system again, keep going, and then it'll eventually come to the zero, and you can't swap it with anything. So that zero stays there, and then it gets deleted. So we'll end up with our final algorithm of 1, 2, 4, 5, 6, 8. So essentially it just swaps the zero with the last number, and then reduces the number by, then reduces the list by 1. So it moves all the zeros to the end and cuts them off. Okay, next one is binary search. And the binary search algorithm will essentially, it's like a tree in which if it'll essentially look at, if it will have a set that's ordered. Okay, so if I have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, let's say I'm trying to eliminate all sixes from my set. Essentially what the binary search algorithm will do is let's try to eliminate nines. So what it'll do, the binary search algorithm will do, is it'll essentially create two partitions. It'll go through the first list and the second list. Okay, it'll create two partitions, so list 1 and list 2. I'll go through the first list and be like, okay, 1, 2, 3, 4, 5 exist here, and 6, 7, 8, 9, and then 10 exist here. And I'll look at this and be like, well, there's nothing, 9 doesn't exist in this first list, so that's not what I'm looking for. So I'll come down here, make this list 1, and it'll go through this list again. It'll take this list and make a partition out of it. So it will take this new, quote unquote new list that it's formed and go and say, okay, so list 1 equals 6, 7, 8, or 6, 7, or it won't matter really. And list 2 will be equivalent to 8, 9, 10. Again, I'm going to be like, okay, well, 9 isn't in list 1, so I'll go ahead and delete that. And I'll look through this again, and it'll split this list. So it'll come here and split this list. Now it's only looking from that original set of 1 through 10 that we had, it's reduced it down to 8, 9, and 10. So the algorithm will again go, okay, list 1 equals 8 and 9, and list 2 equals 10. And it'll look and be like, okay, well, 9 exists in this list, so I finally found my 9. And I have found it, and that's all I need. Since this isn't a data sorting algorithm, it's just a searching algorithm. Keep them, it's just a binary search. Okay, so in essence, binary search bounces back and forth between between a shrinking list and checks every smaller list made to see if the target value is in it. And like I said, my notes will be posted on my website. So, if something doesn't make sense, then you can go ahead and check that. The next and the last one that we have to talk about will be the pattern searching algorithm. The pattern sorting algorithm is quite simple in that when you have some value, if you have some pattern, if you have some text, right, it'll be like A, B, C, A, B, C, D, E, B, and then F, right? If I have to search for C, D, E, then what I have to go ahead and do is, let me title this real quick. What I have to do, what the algorithm will do is it'll go through this list and be like, hey, does A and C match? And since A and C doesn't match, it'll move on. Be like, does B and C match? No, it'll move on. Does C and C match? Okay, cool. Does C and C match? Since C and C matches, it'll move on to the next term. So it's like, does A and D match? No, it doesn't. So it'll reset. It'll go back to B and be like, does B and C match? No, it doesn't. Does C and C match? Correct. Does D and D match? Correct. And does E and E match? And then as a result, it has found that, hey, this is what you are looking for, right? And yeah, so here, so these are a list of so all of these are these data editing or sorting, these data editing or deletion or identification algorithms, whereas the bottom two, binary search and pattern search, are just finding things. It doesn't have to delete it. So now we get on to an interesting point, which is what happens if you can't polynomially map that algorithm. So like we talked about way up here, if you have an algorithm that's polynomially determinate, you can write an equation to say how many steps it'll take. And if we come down here, it's like, what if there's so many steps or an infinite number of steps that you can't plot it? That's when you get into indeterminate algorithms. So intractable algorithms, intractable solutions. And something with an intractable solution is an example of an intractable solution is called the Hamilton circuit. So the Hamilton circuit will essentially be like, hey, if I need to get from A to D, what are the number of steps I can take? Or if I need to get from A to D, what are the number of steps I can take to get there? Well, it's simple on this small scale. As we start expanding it up to things such as the world, if you have a map, right, there's technically an infinite number of ways you could get from your home to school. Taking one right versus taking one left, crossing one street versus crossing another street. There's an infinite number of ways you can take it. And so to solve these problems, there's no like mathematical way. You just have to brute force it. You would just have to try every solution until you find one that's satisfactory and keep it. So yeah, that should be it. So essentially what you need to know from chapter 3 is that an algorithm must be easy to understand, must be elegant, it must be efficient. Efficiency is measured in time generally. The amount of time that it takes can be mapped by a polynomial function. If it can be mapped by a polynomial function, it's called a polynomially determinate function. Polynomially determinate functions include data editing algorithms, such as the move everything left, the selection sort, the copying over algorithm, and the converging pointers algorithm. Additionally, there's things like binary searches, which are also polynomially determined algorithms, but they're just for searching. Binary search and pattern searching. They just search, they don't actually edit data. And on the off chance that you cannot polynomially map out your equation or the number of steps it'll take for your algorithm to finish, you'll have to go ahead and call it an intractable algorithm or an intractable solution, because there's just too many possibilities. You can't mathematically map out the number of possibilities that it has. That should be it. I will be posting my notes as well, so go ahead and check those out. This audio will be unedited because I don't have time, but people want me to make this video. Next one will be better. Yeah. Good luck.